Hello, welcome back. I'm Jason. Today we're going to talk about the difference between AC electricity, alternating current, and DC electricity, direct current. Specifically, I want you to be able to visualize with a real demo that we're going to do here how alternating current actually works. And in the process, we'll talk about how it compares with direct current and why we even have two kinds of electricity to begin with. Why do we even have them? So here is a regular light bulb. This is not an LED bulb. This is an incandescent light bulb. So inside of here is a filament made of tungsten. And when we put electricity through here, it lights up. Now, it gets hot and it lights up. So I'm just going to screw this in here. And there's two wires in the cord leading up to this thing. And so electricity will flow through. Let's go ahead and turn it on. All right, so here is our big demo. We turn it on, of course it lights up. Now this is a frosted bulb, so you can't really see the actual filament inside, but in just a minute I'm going to show you the same thing without a frosted bulb. Now if you look at this, obviously you can hurt your eyes, so don't stare at it for too long. But to my eyes, this looks like a very constant brightness, right? But what if I told you that all of the electricity in your house that you actually plug into the wall, not batteries, I'm talking about electricity coming out of the wall socket, that's what we call alternating current. In other words, that electricity actually comes out, but then it turns around and goes back the other way, and it alternates back and forth, very, very, very fast. So the electricity that's flowing through this wire is going through the bulb, and then in rapid time, it turns around and goes the other way. And so alternating back and forth through this wire, I'll draw some pictures in a minute for you to visualize, the electricity is alternating back and forth in time. How fast is it going? 60 times every single second. So what I'd like to do is pull out the high-speed camera, really get on top of this thing, and show you what it looks like when we slow down time for a light bulb with alternating current. Now this is around 1,400 frames per second, and you can clearly see the pulsating nature of the light coming out of this light bulb. Let's get just a little bit closer to get on top of it. Honestly, I find it kind of mesmerizing to look at, and it's kind of amazing to me that we can't see this with our naked eyes because our eyes are just not fast enough. Now here's the same light bulb, but the frame rate is cranked up to about 3,500 frames per second, so you can really see the pulsating a little more clearly. Also, I had to play with the lighting quite a bit, so I turned down the studio lights so that you could see a little bit more of the internal glowing from the filament. So here are two light bulbs side by side. You can clearly see that the pulsating is in lockstep with each other. And that's because all of the outlets in your house have the same frequency of the voltage waveform, and also they're in the same phase. That means the crests and the troughs of all the outlets on a single circuit are all lined up with one another. So that's why the pulsating is in lockstep. I have a different kind of light bulb here. And this light bulb is the same sort of deal. It's an incandescent light bulb, and the only difference is it's not frosted. So we can really get on top of this filament. It's a clear filament there. Now don't forget, inside of these light bulbs is a partial vacuum, right? So everything's getting very hot in there. You don't want gas in there to overpressure to expand and explode the bulb. So there's a partial vacuum. That's why when light bulbs break, you hear that kind of like that weird popping sound. I can't describe it, but it's very, very different, very, very weird. It's because there's a partial vacuum inside of there. And these light bulbs glow because of black body radiation is what it's called. When things get hot, they emit photons. Even your body is emitting photons all the time, even now, but mostly in the infrared. When we heat things up a little bit above room temperature, they begin to glow in the visible, mostly in the red end of the spectrum first because it's closer to infrared, but then getting and changing colors as you make it hotter and hotter. So what I'll do now is I'll turn this one on just to see if we can see any difference. And of course, you don't see the outer layer here glowing so much because it's not frosted there, but you can see the filament super, super white in intensity. And again, when I look at it briefly, because you don't want to hurt your eyes, again, I don't see any flickering at all with just my senses, right? So let's slow this down and see what we can learn about it in slow motion. Now, I think this is really, really cool. I was able to get my high magnification lens out and really take a look at that filament. And you can just see the filament itself pulsing and glowing. Now, it took me a while to get the best shot. What I ended up doing is basically turning the studio lights more and more off and adjusting the exposure to really looking at the filament itself. And once you did that, at the very end here, the last few shots really show the intricacies of the filament and exactly how it glows, which I think is actually really cool looking. And the other thing that's interesting is if you look really carefully, you can see the filament itself moving. Not only is it pulsating in the brightness, but you can actually see it like almost like a shaking chain or a shaking necklace or something, jiggling up and down as the thermal expansion and contraction of the metal happens. You can see it physically moving, which looks really cool. And I'll just say that I know almost nothing about how light bulbs are actually made, but when you get on top of this filament, it's not a straight wire there. It's wound in a coil, but also when you look at each kind of helix of the coil, it looks like it's almost like a miniature spring or slinky kind of like on each helical region there. So there's just so much detail when you get up on the microscopic level that you can really see. There's the linear aspect to it, then there's the rotation around some sort of direction, and then along the coil itself, it seems to be like this compressed slinky or caterpillar looking thing. So the construction of these coils is quite amazing. Now, science is all about learning, right? I learned something here that I did not expect. I sort of expected to see this filament pulsating a little more dramatically than it did. I mean, we absolutely did see it in slow motion pulsating like that. We'll talk about the reasons why in just a second. But it seems like the frosted bulb seemed to be a little more impressive. And I couldn't figure out why in the beginning, but after thinking about it, I think I know the reason why. So I mentioned black body radiation. Things heat up and then they begin to emit photons, okay? So when you're looking through this glass, through the clear glass, directly into the filament, what's going on is the frequency is so high that it's oscillating back and forth, up and down very, very, very fast. But in between cycles, the filament doesn't have time to really cool off very much. It does a little bit, but not very much. And so the amount of photons that come out of it is related to its temperature. And since everything is changing so fast, you don't really see it as pronounced as you might think, because in between the cycles, when the wave goes up and then down and then back up again in AC, we'll talk about it's a sine wave. So when it crosses through the 0 point, the filament is still really hot from the previous cycle. So it dips a little bit in terms of intensity, but maybe not as much as I were to think. But when we look at the frosted bulb, we're not able to see the filament. We're only able to see what photons are hitting the inner part of this light bulb here, the frosted area on the inside. So we're not really seeing the filament directly, we're seeing the indirect effects of it impinging there. So it's not so much related to, I mean, it is related to the temperature of the filament, but I think we're able to see it a little bit better because the filament is always really, really hot. It does go down and it does go up, but it's really, really hot all the time. And so we can't see it as pronounced. Whereas by looking at the interior of the frosted part of the bulb, we're really just seeing an indirect indication of how many photons are hitting the bulb. And so we can see it a little bit better. So now in your brain, you should have a mental picture of what AC electricity really looks like, right? From a physical principle of a light bulb getting brighter and dimmer over time. But I'd like to dive a little bit deeper to get a little bit more of an understanding as to what's really going on here, okay? Now I mentioned in the USA, it's 60 hertz. Now the unit of hertz is cycles per second. So that means the electricity is switching directions and going through a complete cycle 60 times every second. Now I want you to think about that for a second, right? There's a second, there's a second, there's a second. Every snap of my fingers, the electricity has switched directions 60 times. That is really fast, and that's why we can't see it. Our photoreceptors, our chemical receptors in our eyes are just not fast enough for the chemistry to react to the fluctuations in the photons. We can see it in the slow motion camera that there is more photons and then fewer photons, more photons and fewer photons. But our chemistry in our eye is just not sensitive enough to detect those really rapid fluctuations. You can almost think of it as sort of like our eyes are sort of averaging all the time, averaging the brightness of the scene. And because it's switching directions so fast and going bright and dim so fast, what we see when we look at a light bulb is kind of like the average intensity over time. Now, in other parts of the world, the frequency of electricity is a little different, but in the USA, which is where I live, it's 60 hertz, right? In other parts of the world, it's 50 hertz, that's 50 times a second, and so on, right? Now, what does this actually mean? We're going to draw a picture in just a second, and I'll talk about the voltage and the current and stuff like that. But if you consider this time, and you consider this the voltage, you always hear about how many volts a circuit has, right? We'll talk about voltage in just a second a little bit more. What's going on here is for direct current, which would be like a battery or just like any kind of like a constant source, the voltage over time would be constant. That's what a direct current is. So in direct current, if you hook up a battery to a light bulb, it looks like a constant intensity, and it really is a constant intensity. I thought about putting that in the slow motion camera, but you're just not going to see anything because it's not going to change. So it doesn't really show you anything. But for direct current, the voltage, and because of that, the current over time stays constant. So it will be a flat line here. But for AC electricity, it does something like this. It goes up, and then it goes down again, and then it goes up. That is what we call one cycle, but it doesn't stop there. It continues on, and then it goes like this, and I'm running out of board, but basically it continues on. And you can see that as it goes up to a maximum, down to 0 volts, this is 0 volts right here, and then down in the negative direction, we'll talk about negative in a second, and then back up to the starting point. See, here it would be going up again. Then this is called one cycle. So when I say cycles per second, I mean one complete repetition of the waveform where it begins to repeat its upward journey. Again, that's called one cycle. And the frequency, as I mentioned, is 60 hertz, which the unit of hertz is 60 cycles per second, 60 cycles per second. Now, if you ever took a physics class, you're going to talk about frequency and period, right? Before we do that, let's talk about what's happening here. As the voltage coming from the wall socket is going higher and higher and higher, then it pushes more electric current out. So don't forget, voltage is what we call the push. It's called an electromotive force. It's like the push that pushes the actual electrons or electric current to flow around the circuit. So voltage is the push, but current is the actual flowing of the electrons, right? So when you push on something, then you expect something to move. So the voltage is doing the pushing, but the electrons are doing the flowing. You can think of electrons being like water in a river, and maybe the height of a mountain, if it's coming down a mountain, or the pressure in a hose would be like the voltage. So voltage is the push, current is the flow. And resistance, for those of you who know Ohm's law, is how much resistance to the electric current we have in the circuit. This light bulb is resisting electric current flow to a certain degree. And we can change a light bulb, we can make it brighter and dimmer by changing the resistance inside of there. All right, so anyway, as we increase the voltage, then more current begins to flow because we're pushing more, and so more current begins to flow. And so as more current flows, the light bulb gets brighter and brighter and brighter until we reach a maximum voltage and a maximum current and a maximum brightness of the bulb. But then the current is still flowing in the same direction, but it's going down now, down, 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 and so it's less current and less voltage, and eventually it gets to 0 very momentarily, and the brightness of that bulb is at its minimum value. But if you notice, when we looked at the light bulb, it didn't go like bright and then to nothing, and then bright again. It didn't do that. Why did it not do that? Well, because even when the current is going through 0 and there's no current momentarily flowing through the light bulb, the filament is still hot. Remember, why is it glowing at all? It's because of heat, because of black body radiation is what I was telling you. So everything glows at a temperature. You put a hot poker in a fire and it glows red. If my body is glowing in infrared. So even though the current momentarily went through 0, the filament is still very hot, so it's still glowing, and that's why it reaches a minimum intensity, but it doesn't go to 0 because the thing is still hot. Now, if I turn the light bulb off and let it sit for a few seconds, then it slowly, you've all seen the light bulb go out before, it slowly dims and then eventually stops glowing. However, it's glowing in infrared for many minutes after you shut it off, and then when it reaches room temperature, it's still glowing in infrared, but just not as much. So when we get here, we're glowing less and less, but then the voltage switches direction. And that means the current also flows in a different direction. And so if you wanted to look at that, I'm going to draw a picture, but what that means is the current might be flowing through this wire, and then through the bulb, and then back through this wire, but then it stops, and then it turns around so that the current begins to flow this way through the far wire, and then back this way. Then it switches to go this way. So it's like a dental floss. It's like you're flossing, and that's what's happening 60 times every single second. Now, it's 60 cycles per second, and for those of you who have taken physics, you might have learned about the period, right? The period is defined as 1 over the frequency. This is how many seconds it takes to repeat. Well, the reason it's 1 over f is because it's 1 over 60 cycles per second. That's all you're doing when you take 1 over 60 cycles per second. But remember, how does this work mathematically? What this means is that the period, the number is just going to be 1 over 60, and the units, remember, when you have a fraction divided by a fraction, you flip and multiply, so it becomes seconds on top and cycles on the bottom. Flip and multiply, right? So whenever you do the 1 over 60, when you do that in a calculator, you get 0.01666 repeating on the sixes, which is approximately equal to 0.0167. I'm just rounding it now. And what is the unit here? It's seconds per cycle. So what we're basically saying is that the frequency is 60 cycles every single second, but another way to represent that is 0.0167 seconds occur for every cycle. So the period is expressed in seconds. It's how long does it take for the thing to repeat. Now, 0.0167 is a tiny fraction of a second. That means that the electricity switches direction. It takes that long to switch directions, to begin to repeat everything over again is what I'm trying to say. That's a better way to say it, to begin to repeat the cycle again. And that is such a small fraction of a second that we just don't notice the pulsating that's going on. And if you want to turn this into milliseconds, you can move the decimal 1, 2, 3. That's going to be 16.7. Again, that's rounding milliseconds per cycle. So when you see the period expressed in milliseconds or seconds, it's really seconds per cycle. And that's what, in other words, that's the distance in time. Notice this is the time axis. So the distance right here, 1 cycle, and that would equal 16.7 milliseconds. Of course, that's a rounded number. And that's a really, really, really tiny time. And then the next cycle takes this long to occur, and the next cycle takes that long to occur, and so on. So you can express it in terms of frequency, 60 cycles per second, or as a period, this many milliseconds or this many seconds for every cycle to happen. All right? So that is what I wanted to talk about as far as the waveform, and that is a sinusoidal waveform. Notice that shape. It's not a half circle. It goes up steeply, then it reaches a maximum, then it comes down, and it's kind of steep, and then it comes back. That's called a sine. This is a sine. A cosine has the same shape, and you might have learned that back from algebra or trigonometry or calculus back when you took those things. I'm going to explain to you actually why this shape is the shape of it in just a second, but before I do that, let's draw a quick little circuit here. It's a circuit anybody can understand. Let's first talk about DC, because it's helpful to compare and contrast. So if I had 120 volts as a DC, that means that direct current means nothing changes over time. And if I had a circuit connected to a light bulb, it would look something like this. This is a symbol for a light bulb. Actually, there's a couple of different symbols of light bulbs, but that's a symbol that you see very often. All right, and so you might see little symbol here for light coming out, right? And so what's going on here is there's a positive and a negative terminal. Now, out of the negative terminal is where the electrons come and they jump from atom to atom and atom all the way around, almost like a chain reaction back to the source. Then they come back through the source and they go back, and it makes a circuit, and they just keep going over and over and over and over and over, and they never change directions. Now, in engineering, even though the electrons do flow this direction, we actually choose, it's just a sign convention, we choose to show the electric current flowing out of the positive terminal in the opposite direction from the electrons. Now, if you don't like that, fine. Think about electron flow, but I'm just telling you that when you get into circuits and you actually learn about it in detail, then we don't talk about electron flow too much, even though that is actually really what's flowing. And the reason why we don't talk about it too much is just because electrons are negative, okay? And so it ends up making all of your equations have negative signs everywhere. It's a convention somebody decided a long time ago. It turns out that a negative charged particle going this way behaves mathematically the same as a fictitious pretend positive charge coming out and going the other way. So it's a mathematical trick. We say the current comes out of the positive terminal even though there are no positive charges flowing, because mathematically that's the same thing as a negative electron flowing in the opposite way. So in all of diagrams and circuits, you'll see the current written this way as a positive flow, even though the negative charges go the other way. So this is DC, and there's no pulsating. The light never changes intensity or anything like this. Now, let's look at AC. Alternating current, right? So instead of plus minus, you could put plus minus there, but often what you see is a little sine wave inside of there to remind yourself that this is an alternating current source. So what you have is a light bulb, which I'll just draw, same story here. There's your light bulb right there. Okay, now this thing is alternating, so which way is the current coming? Well, what you do is you pretend at time 0 that the current begins to on the positive side, just like the voltage here. And what you do is you draw the current coming out like this, but you know in your mind that that is only true for the very first part, and then it begins to switch directions and the current begins to flow out of this, the positive fictitious current begins to flow out of this way. So what's going on for alternating current is for the first cycle, for this first part where everything's positive, the current is coming out this way. It's getting bigger, 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 then it reaches a maximum, and then it gets smaller, 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 but it's still going this way. But when we cross this line and go this direction, the voltage is negative, and so the current is also then negative. Negative current just means the current flows the other way from the way I've drawn it here. So in the beginning of a wave, it goes this way, but then it slows down and stops, and then it goes back the other way through the source flowing this way. I would draw an arrow going this way. And then it slows down and stops, and then it would come this way. So what's going on is really and truly like dental floss. If you could grab the wires, or if you could grab the electrons in the wires, then it would be like, and how fast would that be? One cycle would be 0.0167 seconds, which is 16.7 milliseconds, which is really, really fast. So as the current begins going this way and reaches its maximum, the light bulb gets brightest, and then it starts to decrease in value, eventually reaching 0, and then it begins to go the other way. And when it goes the other way, it's still going to be heating up this filament the same as if it were flowing this way. If the electric current goes this way through the filament or this way through the filament doesn't care. It's going to glow in a similar way, in the same way. So it gets brighter and dimmer as this current does the dental floss thing over and over again, and that is happening so fast that we can't actually see it. All right. Now, the question everybody has that you'll understand this concept. The whole point of this is I wanted to tell you what AC electricity was, but I wanted to give you a concrete, feel it in your bones kind of understanding of it, right? So I wanted you to see something, and then I wanted to explain something to you. But the natural question that you have, that everybody has, is why do we have two kinds of electricity, right? Why do we have an AC and a DC? Why don't we just have AC all the time? Or why don't we just have DC all the time? Well, way back in the early days when all of this stuff was invented and really begun to be understood, there was a big argument about what was better, AC or DC. Nowadays, we don't really take sides too much because we have applications for both. So here's the big picture. AC electricity is easier to generate in large-scale reactors, either a gas plant or a nuclear plant or a coal plant. Any kind of large reactor like that, it's actually easier to generate AC electricity. I'm going to show you a picture in a second why, right? However, I don't want to say DC is worthless. DC is very important too. If you need a portable power source and you don't have a reactor, I mean, maybe you have just a small drone or a phone, right? Or a small device like a remote control. Well, a nice battery that is a DC device, a battery is a DC device, is going to be better because it's portable, right? So batteries are more portable. You don't require this gigantic reactor, and they're very much used all the time. We use batteries in phones, batteries in computers, batteries in almost everything. And they're very good for portable devices. Even cars nowadays, electric cars, that's a DC device too. That's a DC battery in there as well. So solar generation, when you have solar panels generating electricity, guess where the electricity goes during the daytime? Because the sun doesn't shine at night. So you always generate more electricity during the day than you need. And so what do you do with it? You put it in batteries. So when you have these solar farms generating electricity, it always comes with batteries, which are storing the electricity during the day. The excess electricity goes into the battery, and then at nighttime, the batteries are drained to feed the houses. And then during the daytime, the cycle repeats again. So anytime you use solar panels, that's DC. Anytime you use laptop, phone, any portable device, remote control, that's DC, right? But for large-scale production of power using a reactor, like a nuclear reactor or a coal reactor, it's going to be much easier to generate with AC. And also, it's easier and better to transmit electricity over long distances with AC, alternating current. I'm not going to go through the math right now, but whenever you transmit electricity over long-distance power lines, those power lines are made of wires. And even though we say wires conduct electricity well, if you put 1,000 amps through a wire, which is the electric current, put a lot of current through a wire, it heats up. And when it heats up, that's wasted energy. This light bulb, we know I can turn it on again for us here. When I turn this light bulb on, electricity goes in and the filament gets hot. And what happens? Well, the energy goes into heating up the filament, and the filament radiates photons away, and so I'm losing energy. Some of the energy coming in through the wire gets literally converted into photons and gets lost from the system. So the same thing is happening with power lines. Except with power lines, I'm not heating up the wires so much that they're glowing, but I'm still making them hot. And anytime you make them hot, it loses energy. So for DC, it turns out when you go through the math that you cannot transmit electricity over very long distances very easily with DC electricity. For small scale, it's fine. For large distances, not so good. For AC electricity, not only can you generate it a little bit easier, and not only can you transmit it long distances a little bit easier, but you can remember this voltage here. This voltage for an AC is usually referencing the peak up here or peak down here, the peak voltage, right? You might have heard of 120 volts in your house. You might have heard of 220 volts in the house. There's some other stuff in there I don't want to get into called RMS voltage, but you can still think of it as the peak to peak voltage, right? That's the amplitude is the voltage you care about. When we transmit electricity over long distances, it's more efficient if we do it in thousands of volts. And the reasons why have to do with heating up the wire. Now, the problem is, how do you get how do you get up to that very high voltage like that? And when you get down to the houses, how do you take it down to a very low voltage that's safe for people to be around, right? And that is using the concept of what we call a transformer. A transformer, it only works with AC electricity, and it uses magnetic fields in a primary winding and a secondary winding to step up the voltage to very high voltage and to step down the voltage to very low voltage. So the reason we have AC electricity so predominant in everyday life is because it's easier to generate. And then when we want to transmit it, we can step up the voltage with a transformer, only we can do that with AC, into very high voltage for transmission across the wires without very much losses. And then when we get to the houses, we have transformers that can step it down to the substation, not directly to the house, to the substation and to the neighborhood. They're stepped down to these low voltages that we can use. So it's easier to manipulate the voltage. When you have a DC system, you can't really easily step it up and down. I mean, there are ways to do it, but it all involves temporarily converting it to AC and then back again, and there's more losses there. So those are the main differences, and that's mostly why AC is around, even though DC is so much more portable and convenient for laptops and things of that nature. The last thing I'm going to tell you about is, why does this AC signal have this shape? Why is it a sine wave? Why is it that special shape that we learned in algebra class? Well, I'm not going to get into every last detail of the theory, but I'll show you this one little piece of it here. So this is a cartoon. It's not accurate, but it's enough for you to understand of an AC generator. So I tell you, my mind was blown when I first learned, when I was younger, that when you have a nuclear power plant, all the nuclear physics going on there, the only reason we have the nuclear reaction of whatever nuclear fuel is used is really just to make a hot source. And that hot source heats up water, and that water is converted to steam, and the steam goes and turns a generator, which is this thing, okay? And it generates AC electricity. Now, if you don't have a nuclear power plant, you might have a coal power plant. You shove a coal in there, but the coal is only used to heat up a boiler, to heat up water, to turn into steam, to turn a generator, right? And then if you're not using coal, you're using gas, right? So the gas is only used to make a hot source, to heat up water, to turn into steam, to turn a generator. And I was kind of let down by that because I thought nuclear reactor was some kind of like Star Trek thing. It just turns out that nuclear reactor is a really efficient way to make a lot of heat in a small space. And you got to be careful because of nuclear physics, and talk about that one day. But basically, it's only there to make something hot, to turn water into steam, to turn this thing. And so all of our large-scale production of electricity, even the hydroelectric with the water coming over the dam, it's just used, that water is used to turn a generator, which is this thing on the board right here. So it's efficient to do this because the way it works is something called Faraday's law of induction. So what this means is Faraday developed a law that basically said if you have a magnetic field and you have a coil of wire or a loop of wire in the magnetic field, and you turn the coil inside the magnetic field, make it move, which is what a generator is, then you generate a voltage. And that voltage is what we use to power everything, right? So it's not free energy. You still have to turn this thing somehow, right? So for a waterfall or a hydroelectric, the flowing of the water turns it. And so that comes from gravity and other things, snow melt and stuff like that. So it's not free. For a nuclear reactor, it comes from the heat to make the steam, and the steam expands and it turns this thing. So it's not free energy, it comes from somewhere, but that's how we're generating our electricity. We're turning a coil of wire in a magnetic field. It's exactly the opposite of a motor. A motor, you turn on the electricity and then you force the thing to turn inside of the magnetic field. For a generator, you do it backwards. You turn the wire through some mechanical thing like a hydroelectric or nuclear plant, and then that generates what they call an EMF, electromotive force, which is the same thing as a voltage here. Now, why does the voltage have that sinusoidal shape? The way it works is you have a magnet here and another magnet here, a north pole of this and a south pole of this. Now, it would be helpful if you to visualize a magnetic field going between these magnets with an arrowhead right here, right? Something like this. And you can imagine thousands of these little invisible magnetic field lines that go across from one side of the magnet to the other. And you can imagine this loop of wire being inside of this magnetic field. And you can imagine that magnetic field, the word we really use is called magnetic flux. Flux just means those arrows, those magnetic field arrows, right? And what you can imagine is these arrows cutting through the cross-sectional area of my loop. Now, I've only drawn one loop here, but actually in real generators, there's thousands of loops, and they're all on top of each other because the more loops you have, the more magnified this effect is. So Faraday's law basically says, if you have these flux, these magnetic field lines, the way I've drawn it here, because it's flat, there's really no flux going through the loop itself. But if I were to turn it like this, so the loop was up and down like this, then you can imagine all of these lines cutting through the loop, and you would say that there would be a lot of flux cutting through the loop. Now, Faraday's law basically says that when you turn this wire, this loop in a magnetic field, you generate a voltage. And the voltage is going to be proportional to how the flux is changing as it cuts through the loop. It's a little confusing. It's not proportional to how many lines are going through. It's proportional to how many lines are changing over time. It's all about change. And for any of you that's taken calculus, it's all about the derivative. It's all about change. So it's not giving you a voltage proportional to how many lines are going through at any given time. It's giving you a voltage proportional to how fast those number of lines are changing over time. So as this thing rotates, it's constantly changing how many lines are going through the loop. Here, there's no lines at all. Here, there's a maximum number of lines, and anywhere in between, it's cutting through or allowing less or more of these lines to flow through this loop. And over time, how the derivative or the rate of change of these lines cutting through this thing is what generates this voltage. And when you draw it and map it out, it turns out that it turns into this sinusoidal shape. And so for those of you who just want one more nail in the coffin of figuring out why it's exactly the shape, if you remember from math class, the sinusoidal shape comes from what we call the unit circle. And the unit circle, the sine function was the projection as you rotate around the unit circle, it was the projection onto the y-axis. It's literally like a shadow projection on the y-axis, and the cosine function is the shadow projection onto the x-axis. So what I'm trying to say is you learned in math class that sine and cosine functions come from circles. And this loop of wire is turning in a circle. It literally is rotating. So yes, the thing I've drawn is a square there, but the turning is turning in a circle. So it's not a huge surprise that if sines and cosines come from the unit circle, and I'm turning this coil of wire in the unit circle, then the voltage you get from Faraday's law is going to be a sine. And that is why the voltage that we get from generating electricity from this kind of method is a sinusoid. And because it's a sinusoid, then we can use transformers to step up and down the voltage, because transformers, the same way this induction only works with changing, something changing over time, you have to have an AC electricity in order for transformers to be able to step up or down the voltage. All right, and that is why we have AC electricity so prominently in our houses, because we can generate it very easily using a system like this. We can step it up and step it down and transmit it over long distances without too many losses. And you just have to be careful, because you have to step it down. Otherwise, it's a dangerous voltage that could kill people and things like this. All right, but DC electricity has its uses as well. Deep space probes, a lot of them have batteries. Satellites have batteries. Solar power is going to use batteries. Cars nowadays are using batteries. So it's not like one's better than the other. It's just that they're both different for different applications. All right, I hope you've enjoyed this. I really do. I wanted to show you a concrete example of AC electricity, slow down time, let you get comfortable with seeing the amazing thing that our eyes can just not perceive rapid changes like that. And I'll leave you in the brightness of a light bulb. I will leave you with one philosophical thought you can chew on next time you're walking around just thinking. If our eyes cannot detect the brightness fluctuating of these light bulbs, because of the chemical limitations of our receptors in our eyes, then if we never were able to develop high-speed cameras or slow down time in this way, you would never be able to visualize what I've just shown you today. And you may never know that these light bulbs are fluctuating at all. And the reason you wouldn't know would just be because of the limitations of your senses. So what else is out there that we can't perceive with our limited human senses? What are our senses preventing us from understanding about the universe? Because we're limited by our chemical brains and our chemical eyes and our chemical nerves. What other things out there about space-time, about physics, about extra dimensions, about how the universe is constructed on a large scale, galaxies, gravity? What else is there about the universe that we just can't perceive, so we can't interact with it in a way to help us understand it? What else is out there that we are limited by? I don't choose to look at that negatively and be depressed about it. I'm just trying to say, maybe there are other things out there we have to develop experiments for to help us discover more things, and our eyes and ears are just not going to cut it, especially when you get down into quantum mechanics. You get down into quantum mechanics, things get really weird really fast, but it's only because our senses don't directly interact with single electrons or single photons. So quantum mechanics seems so weird to us. And so I think it's the same kind of thing. This light bulb fluctuating seems kind of weird at first, but then you realize, well, it's because of a limitation of our senses. Again, thanks for hanging out with me. Please drop me a line. Let me know what you think, and I'll see you in the next one. Learn anything at mathandscience.com.